Hi everybody, welcome back. Last class we were discussing about Compton effect, the shift in wavelength as the photon is scattered by electron. And we saw Compton explained the effect, the shift in wavelength, change in wavelength, decrease in energy or the increase in wavelength, the shift in wavelength of a scattered photon using the photon model of the light. So light is considered as a particle, and considering light as particles, he derived an equation for the shift or the change in wavelength. And we saw the change in wavelength depends only on one factor, that is the scattering angle. So this is the equation that we got. Now we want to verify it experimentally. Okay, so the verification also done by Compton and the experimental arrangement that is shown here. So this is the experimental arrangement for the Compton effect. What you see here is a source of monochromatic X-rays. So this is producing X-rays, and we need a fine beam of X-rays. So we use collimators. So these are the collimators these are the collimators. Okay, these are actually lead blocks. So they allow only a beam to pass through it, and that falls on a target. So this is the target. Okay, so this X-ray beam passes through this target. Compton used carbon as a target, and we have a detector here, an X-ray spectrometer, which can detect the radiations coming in at different angles. So this detector or this X-ray spectrometer can move over a circle, so it can record, detect X-rays coming at different scattering angles. Now, as we see here, this is the experimental arrangement. The beam of X-rays of non-wavelength, we know this is monochromatic, so we know the wavelength of the X-ray photon, and the wavelength of the scattered photon is determined using X-ray spectrometer. So this is what we get. We record the intensity of the X-ray coming at the different wavelengths at different scattering angles. So first we take the phi is equal to 0. What is phi equal to 0? Phi equal to 0 means you are detecting the light coming straight or in the initial direction of the X-ray. Okay, so this is phi equal to 0 when X-ray spectrometer is here. So that is recorded, and here we see we get only a single wavelength. Okay, we get a single wavelength, and that wavelength is equal to the wavelength of the monochromatic X-ray source that we have used, monochromatic X-ray. So delta lambda, there is no shift in wavelength. So delta lambda is equal to 0 as predicted by the formula. The formula, we have this lambda prime minus lambda equal to lambda c 1 minus cos phi. So as this cos phi 0, suppose phi equal to 0, you know this cos phi that will be equal to 1. And what happens? Lambda prime minus lambda prime, lambda prime minus lambda, that will be equal to 0. So there will be no shift in wavelength. So that is observed here. So there is no shift in wavelength. So delta lambda is equal to 0. That is experimentally observed. Then we vary phi to 45, or we observe the scattered radiation at an angle of 45 degree. Okay, then this angle is 45 degree. So the observation is like this. We get two peaks. What we have taken here is the relative intensity, and here the wavelength. We are getting two peaks, one here, one here. We are getting a peak here, another peak here. Okay, that means it consists of two wavelengths, and this delta lambda that can be determined. Then they did this here for phi equal to 90 degree. Okay, phi equal to 90 degree, and phi is 90 degree. You know, here if phi is 90 degree, the cos 90 that will be equal to 0. So lambda prime minus lambda, that will be equal to lambdas. Okay, lambda prime minus lambda is equal to lambdas, phi 90 degree. So when phi 90 degree, there will be a shift in wavelength. We have two peaks here, again two peaks here, one here, another one here, and this is the shift in wavelength, and that is the shift in wavelength is observed here. Okay, now for phi equal to 135 degree, this is for phi equal to 135 degree. The shift again increases. We see the shift increases as predicted by the formula. And you know, the shift will be maximum. As we increase the scattering angle, the shift is increasing. Okay, for phi equal to 0, shift is 0. And as we increase the scattering angle, the shift is increasing. And the shift becomes maximum for phi equal to 180. Okay, so the shift becomes maximum for 180 degree. Okay, this shift that becomes maximum 180 degree, because for cos 180 we know cos 180 is what? Minus 1. Okay, cos 180 is minus 1. Then what will be delta lambda? 2 times lambdas. This will be our delta lambda now. 2 times the Compton wavelength. Lambda c is the Compton wavelength. So that is the maximum shift that we can get. Okay, phi equal to 180. Okay, so this is what we observe. So the experimental curves that we get, that exactly verifies the equation, the Compton equation obtained by considering light as particles or photons. Okay, so the variation is exactly as the Compton formula predicts lambda prime minus lambda equal to lambda c1 minus cos phi. Okay. Now, at each angle, actually two peaks appear. Okay, we have two peaks here for each scattering angle. Okay, and the shift is changing. Why we have two peaks at each scattering angle? Okay, at each scattering angle, we have the incident wavelength and the scattered wavelength. So why this happened? The reason is the wavelength of one peak, that is not changing. This peak is not changing. This wavelength is fixed. Okay, this wavelength is fixed. That is not changing. Only this wavelength is shifting. The second wavelength is shifting. The reason is while this second wavelength, this one is due to the scattering of photons by free electrons in the target. Okay, there are free electrons in the target. Free electrons are those electrons which are in the outermost orbitals, which are loosely bound to the atom. They can be considered as free electrons. And while photons are scattered by these free electrons, there will be a transfer of energy from photon to the electron. And that's how we have less wavelength for the photon. We get the second peak. Okay, so we are getting the second peak this due to the Compton effect, the scattering of photons by the electrons. The electrons are the free electrons or the loosely bound electrons of the atom. Now, why this peak, the first peak, which is the incident wavelength, which is observed at all scattering angles? Why? It is because of the scattering of photons by the inner electrons of that. Okay, the inner electrons of the atom, these are very closely or which are very tightly bound to the, these electrons are very tightly bound to the atom, the inner electrons. So the first peak corresponds to, or the incident wavelength corresponds to the scattering of photons by very tightly bound inner electrons of the atom. Okay, these atoms are so tightly attached. Sorry, these electrons are so tightly attached to the atoms that photon scatters. The photons are scattered by the electrons, but the photons do not lose energy. Okay, during this scattering, photons do not lose energy because the electrons cannot move. They are very tightly bound to the atom. So this explains the first peak, the incident wavelength at all scattering angles. These are the wavelengths of the photons scattered by the electrons in the inner orbitals, which are very tightly bound to the atom. Okay, so that is about the Compton effect, and the Compton effect clearly confirms the photon model of the light. Now the question arises, what is light? The question is this, what is light? In our textbook, you can clearly see this question, what is light? The answer is both wave and particle. Okay, both wave and particle. So why we are saying so? We need wave theory to explain effects like interference, diffraction, polarization, etc. That can be explained only by using wave theory. But to explain some other effects like photoelectric effect or black body radiation, black body spectrum or Compton effect, what we need is the quantum theory, where we are considering the light as a particle. Here we are considering light as wave. Okay, here we are considering light as wave, but here, according to quantum theory, light is a particle having energy hν. Okay, so only then we can explain photoelectric effect, Compton effect, or black body radiation. But we need wave theory to explain interference, diffraction, polarization, etc. So the question, which theory are we to believe? Okay, so which theory are we to believe? So that is the question, because wave theory considers light as spread, the energy in the light is spread out continuously through the wave pattern. That means light is a wave. But quantum theory according to this, says it consists of individual photons, each small enough to be absorbed by a single electron. Okay, so light is a particle. So quantum theory predicts light as particle. So the question is, which theory we believe? Okay, the answer is this. We can think of light as having dual character. That's all we can say. That's all we can understand. We can say light as having dual character, double character. Okay, it has both wave and particle nature. Both nature is there. Both nature is ingrained into light. And wave theory and quantum theory, both theories are required to explain all the effects of the light. They complement each other. Okay, wave theory and quantum theory, they complement each other. Okay, when wave theory is not able to explain a photoelectric effect, quantum theory comes in. Okay, when we need to explain the interference effect, then the wave theory comes in. So both theories are required and they complement each other. So we can say the light has got dual character.